Let's resume. I got a few questions this morning about references on the idea of treating coupling constant as background superfields. So I recommend you to read this classic paper by Seiberg and also the review he wrote with Introductory in the mid-90s. He also, in this review, they also cover a little bit of Seiberg-Witten theory, although quite quickly. So these are really must-read. You know, if you get bored during my lecture, just read those. And you have a laptop, read those. I cannot do any better than this. Okay, so let's discuss electromagnetic duality in the supersymmetric context. So we saw on Tuesday that well, and we will start with the S transformation, which is really the non-trivial part of the electromagnetic duality group. So we saw on Tuesday that we can perform this S transformation as a change of variables in the path integral of an abelian, say, U1 gauge theory, and rewrite the action of the original theory in some dual variables and also with a dual coupling constant. Okay? And this is quite useful because this electromagnetic duality is a strong weak coupling duality, so you can use a weakly coupled dual description to learn about the original description if it's a strongly coupled. Okay, so now we're gonna try to generalize the argument that I gave on Tuesday to the supersymmetric context. And again, we'll just work in the low energy effective theory, which is, contains only abelian U1 vector multiplet. Okay, so we will discuss, so the n equal 2 vector multiplet contains the scalar, say, so we have a chiral A and in the adjoint representation, and then say the vector or the Fotino superfield. So we'll discuss the change of variable for A and B separately. So let's start from the vector multiplet B. Okay, so if you write down the partition function, so the path integral for the n equal 1 abelian effective theory, roughly speaking, it looks like this. So we have a path integral over A, the chiral superfield, and there will be some part of the action which does not depend on B. So for us, this would be, say, the kinetic term for the chiral multiplet A, which follows from a Keller potential. And then we have the path integral over the vector multiplet, n equal 1 vector multiplet. So this is n equal 1 chiral, and this is n equal 1 vector. And so here we have a gauge kinetic action, which looks like this. Imaginary part, integral theta tau A W alpha plus, well, okay, just like this, where W alpha is the Fotino superfield, so this is just expressed in terms of the original n equal 1 vector multiplet, but the usual formula, which I hope you saw during the preliminary course on n equal 1 supersymmetry. Okay. All right. So then, like in the non-supersymmetric context, we had say the analog of V was the photon in mu, A, and then the analog of well, and the analog of W alpha was the field strength at V. And recall that the trick to do the duality transformation was the following. So here, since F was equal to dA, the Bianchi identity, the F equals 0 followed. Okay, and we introduced the Lagrange multiplier to enforce this Bianchi identity for F. And when you do that, then you can path integrate over F directly rather than over A. So we're going to do the same thing here, but supersymmetrically. So here we'll have the same path integral over A, exponential something. And now here we would like to path integrate over, say, W alpha, some chiral fermionic superfield, which doesn't satisfy any further constraint. So this is just chiral fermionic superfield. But, and okay, so we'll have the weight in the path integral to I over A phi, integral before x, imaginary part, integral d2 theta, tau A W alpha W alpha. Okay, but then we want to introduce a Lagrange multiplier that here will be some n equal 1 vector superfield. So this vector and this Lagrange multiplier. Which enforce, say, the supersymmetric version of the Bianchi identity. Okay, and this will look like this. Hopefully, I got all the signs right. Integral before x, imaginary part, integral before theta, the dual, the alpha, W alpha. So the supersymmetric version of the Bianchi identity is imaginary part the alpha, W alpha equals 0. Okay, so this contains the original bosonic Bianchi identities plus superpartners. Okay, so now again there are two ways of dealing with this formula. So one thing is one way is path integrate over this Lagrange multiplier superfield, the dual that will set the imaginary part of the alpha W alpha to 0. So that's going to be the Bianchi identity. And since we're working on R4 that, where there is no topology, the only solution is that W alpha looks like this, and we're back to the original form of the path integral. But the advantage of introducing the extra superfield is that instead, as we did in the purely bosonic case, we can first try to path integrate over W alpha and reduce the original path integral to a path integral over the dual vector superfield. Okay, so now so we will need a few identities. So let's first consider this term here. So we have integral before theta, the dual, the alpha, W alpha. Okay, so we can first integrate by part this supercovariant derivative that is minus integral before theta, the alpha, the dual times W alpha. Then, so this integral over full superspace can be written as an integral over the 2 theta, as well as an integral over d2 theta bar. But as you know, you can convert the integral over d2 theta bar into d bar derivatives. So this will look like this: d alpha d dual W alpha. Okay, and now we act with these two d-bar derivatives on what sits inside the parentheses, and using the fact that W alpha, so W alpha now is does no longer satisfy this Bianchi identity constraint, but it's still a chiral superfield, so it's annihilated by d-bar. So whenever the derivative d-bar hits W alpha, it gives 0. So we can write this, say, d bar alpha dot at 0. So we can write this as integral d2 theta, d alpha, d dual. Sorry, what am I saying? So I'm gonna just fit the d bar square, d alpha, d dual, multiplying W alpha. And so if we introduce a dual K-Geno superfield, which looks like this, but with the vector superfield that replaced by the dual vector, that looks like this term, and we get minus 4 integral e for theta w dual alpha w alpha. For now, w dual alpha is minus 4 squared alpha dual. Okay.
Why can you not integrate over the full space again instead of 1%?
Here, I'm sorry. Thank you. Okay, so now if you look again at what appears here in the exponent, we have a quadratic term in W alpha and then another linear term in W alpha. So again, you can complete the square and do the Gaussian path integral over W alpha. So you do the Gaussian integral over W alpha. What you'll find is that you can rewrite the original path integral as an integral over dA. So here again, we'll have this prefactor that we had before, which did not depend on the original vector field. And then, so we still have a path integrate over the dual vector superfield. And okay, if you do the algebra, what you get is a dual action which looks as follows. W dual is minus 4 squared d. Okay. So what we've done is to replace the original vector field, the vector superfield D, with this n=1 Yang-Mills action by a dual vector superfield with the dual n=1 Yang-Mills action, where now we have a dual coupling. So this will become our tau dual in a second. So we have a dual coupling which is related by the initial S transformation to the original one. Okay, so this was for the dualization of the n=1 vector, which sits inside an n=2 vector multiplet. So now we also want to dualize A, chiral, in the original vector multiplet. So let's see what the dualization of A looks like. So the dualization of A, the scalar in vector multiplet, actually looks is much easier, and is related more directly to this rigid special Taylor geometry that I introduced this morning. So the dualization of A is as follows. So remember that I introduced some dual coordinate to A, which is the derivative of the prepotential with respect to A, and then I have the original A, and since well, you remember the kinetic term. I will remind you of this in a second. But the kinetic term for A and A bar just depended on these two combinations, and so what we want to do is to transform them as follows into dual variables. Which are related by the original variables to the original variables by just its S transformation. Okay? So this will be equal to minus A df by decay. So in particular, we see that we want A dual to be equal to F prime of A, and A to be equal to minus F prime dual of A dual. Okay. So, but now if you remember Legendre transformations, this is nothing but the inverse Legendre transform of the previous one. So this is nothing but Legendre transform, where in particular the dual prepotential is related to the original prepotential in the usual way that you encounter in Legendre transformation. Okay. So very much like when you go from Hamiltonian to the Lagrangian. Okay. So indeed, if you use this relations which follow from the Legendre transform, you can compute the dual effective coupling, as this is going to be, by definition, the second derivative of the prepotential. Okay. But now the first derivative of the prepotential is just this A dual over there, so this is derivative of A dual over A. I think I forgot the minus sign. Sorry, what am I wanted to use this expression over there, so this is so I want to take the first derivative of this expression, so I get minus dA by d A dual. Okay, and this is nothing but the inverse of now I'm just using the formula for differentiation of the inverse function. So this equals then A dual is given by the first derivative of F with respect to A, so this is minus F second of A minus 1, which is also minus tau A to the minus 1. Okay, so indeed if the original prepotential and the new dual prepotential are related by this Legendre transform, which transform the special coordinates as follows. You get that dual effective complexified coupling is the inverse minus the inverse of the original one. Okay? Which is precisely what we wanted here. Okay. So since this is so this Legendre transform is this Legendre transform, since this S transformation looks very much like a canonical transformation, we expect this to have the change of variables to have Jacobian equal to 1. So we expect the measure in the path integral not to change. And so let's instead look at the Lagrangian for the kinetic term of the chirals, the piece which I did not write over there, just to make sure that it transforms correctly. So this is just integral, imaginary part of the integral 4 theta F prime of A bar. Okay, so this was the Taylor potential term. But then if we use the definition of the dual special coordinates here, you can just rewrite this as being equal to minus imaginary part integral V4 theta A dual F prime dual A dual complex conjugate, and this is equal to plus imaginary part for theta F prime dual of A dual bar. Okay. So we end up with a dual kinetic term, which looks exactly like the original one, and okay. And superpotent. Well, so if we put together the two manipulations, the question.
What is the bar over f prime a
Complex conjugate.
Oh, okay.
Okay, so that's also the reason why. So from here to there, I just went to the complex conjugate, and so the final answer looks like the original one, but in dual variables. So if we put together these manipulations that we did for using n equal 1 superspace separately for the vector and the chiral multiplet, which make up the whole n equal 2 vector multiplet, we see that we can rewrite the original path integral in terms of as a path integral in dual variables, which looks exactly the same as the original one, except that dual coupling is related to the original coupling as follows. Okay? And this is exactly the S transformation of the effective coupling that we found in the non-supersymmetric case. Is there a question on this? So I can imagine that, maybe if you're not too familiar with all the manipulations of supercovariant derivatives, this looks might look a bit suspicious, but okay, this is just the supersymmetric version of what I did on Tuesday, so trust me that everything works like that. In fact, there are a few subtleties involved here as well. Let me ignore them. Okay, so next up, we should discuss the central charge formula. Okay, so recall that I think on, well, maybe yesterday, we saw that in the Georgi-Glashow model, in the BPS limit, there was this BPS bound, which related the mass of, BPS bound for the mass of all solitons and all states in the, like, so polyacre monopoles or dyons. Also for all states in the perturbative spectrum, and the bound looks like this. So we derive this bound classically. Where A was the bed for the scalar, which is breaking SU2 down to U1. Tau of U1 was the effective coupling for the massless U1 vector field, and N and M are the electric and magnetic charges of all states. Okay, so this is satisfied by, this inequality is satisfied by all states, and in particular we had BPS states such that the equality was saturated. Okay? And then yesterday, when I introduced n equal to superalgebra, I also discussed the BPS bound. There we derived the same kind of BPS bound, but just from the supersymmetry algebra. And recall that there, the BPS bound had on the right-hand side the central charge of the supersymmetry algebra. And also I told you that the BPS equations follow from requiring supersymmetry. Okay, and again the bound is saturated by short or BPS multiplets. I also told you that, well, okay, because so this bound just follows from the supersymmetry algebra, and so you have two classes of multiplets, either short multiplets which separate this bound, or long multiplets which have mass strictly greater than absolute value of z. But because long multiplets are long and short multiplets are short, I told you that if you have a BPS particle such that its mass is equal to the absolute value of the central charge, even though the central charge and the mass can receive a quantum correction, it will the BPS particle, or the BPS state, will still remain BPS because it cannot. It's a short multiplet, and it could only be it could only become non-BPS if it gain more states, but the states cannot come out of nowhere. So now the question is, what is the formula? So, well, and also, I mean, classically,
sorry,
yes.
They're affected in the same way by the quantum correction, such
Yeah,
that the
in such a way that the relation
balance
still
stays the
holds.
same.
And again, classically, in this n equal 2 theory, you will have a formula which, the formula for the right-hand side will look like this, okay? But this is only true classically, so we're after a formula which expresses for us the central charge of some BPS states in terms of, say, the electric and magnetic charges and the value of A. But we're after a formula which is exact at the quantum level. Okay? So the question that we want to answer is what is the central charge equal to in the n equal 2 theory? And we are looking for an exact formula. So Seiberg and Witten argued for the central charge formula in the following way. So let's first consider some hyper multiplet of electric charge n. So this will couple to the n equal 1 chiral in the vector multiplet in the following way. So there will be some superpotential term which is equal to n times k q tilde, okay, where n is the electric charge. So this just follows from n equal to supersymmetry. And A, again, is the scalar in the n equal 1 abelian vector multiplet of the low energy theory. Okay? So, and then, so in particular, the mass, so this will, you can view this as a complex mass in the superpotential. And this is nothing but the central charge. So for a hypermultiplet of charge n electric charge A, the central charge will look like this. Okay. So now, by electric magnetic dualities, in particular by the S transformation of electric magnetic duality, you also expect that for a monopole of now magnetic charge M, the central charge will look like M, the magnetic charge, times a dual, the dual scalar A, because then the magnetic monopole will carry, will have a dual electric charge M, and so it will couple in a similar way to the dual variables, and this will be the formula. Okay. So then, essentially, by well, I guess by linearity, what Seiberg and Witten propose is the following formula. For the central charge. Okay. And let's also write this as n equal. So now let me add the comment a few comments on this central charge formula. So first of all, it has the correct semi-classical limit. Because say classically, a dual is given by tau times A, so it reproduces the original classical formula that we started from. So the second comment is that this is SL to Z duality invariant. Because remember, I told you that the charge vector Mn transform under SL to Z duality transformation as follows. So M was a SL to Z matrix. And now, earlier I just showed to you that special coordinates instead transform by M rather than M inverse. Okay, so you see that the duality transformation of the charge vector is compensated by transformation of the special coordinates. Okay? So that so another comment is that when I was discussing the possible changes of coordinates in the context of rigid special Kähler geometry, we saw that in principle one could conceive a more general linear transformation where we had some extra constant term here, constant vector on the right hand side. Okay? So in particular, the Kähler potential and all the low energy effective it's not affected by this shift. But now, if we look at this central charge formula, and we know that a dual and A transform, well, okay. So now let's assume that a dual and A transform like this. So can we find the transformation of M and N such that the whole central charge formula remains invariant? And the answer is no. Okay, so there is no way to compensate this shift by C by a transformation of M and N. So we deduce that this constant has to be 0. So I should stress that this statement is only true for the gauge theory without matter fields. In the context of theories with matter fields, the central charge formula is modified. Essentially, here you have some terms which are linear into masses, and then in that case, C is not 0. But okay, we will not discuss this on the rest of the course.
Sorry.
Yes.
Is there any guesswork left in that formula, or do these comments fix it?
Yeah, this is. I think this is really a guess. Satisfies all. All these sorts of requirements.
But couldn't couldn't
And
run-
then it satisfies the fact that if m is 0, you reproduce the original formula. If n is 0, you reproduce also what you expect.
couldn't one do like the opposite reasoning and say, since all what can happen happens, then we should write down the most general thing and prove that it's the only one? Or there is no reason for wondering?
Yeah, that's right. I mean, one could do that, but that's not the way it was argued.
Okay.
And I don't think it was proven in the way that you would like it to be proven. I'm not aware of such a derivation. Okay, so finally, the other comment was that I wanted to make is that you can also deduce that this matrix M lives in SL to Z rather than SL to R because it acts on the charges. So since charges are quantized, the entries of this matrix have to be integer. So that's also the other reason for the discrete transformations there. Okay, so once again, so I should stress that this is this electric magnetic duality. Once again, it's not a symmetry. It's just you should just view it as a change of reference frame. Okay, but still, it's quite useful because the S transformation maps strong to weak coupling, and so this will be used extensively in the following. Any questions on this? Okay, so now then let me start. So from now on, I'll try to explain to you the argument that Seiberg and Witten used to determine exactly the infrared effective action. So, and this is essentially based on rigid special Keller geometry that introduced this electric magnetic duality. Group SLTZ, which acts on charges and special coordinates in this way, and weak coupling results. So we'll try to use this to determine the infrared expected action. So let's start by using weak coupling results. So let's discuss what happens in the weakly coupled region of the moduli space. So recall that the infrared physics on the Coulomb branch is weakly coupled if the VEV A for the scalar in the vector multiplet is much larger than the strong coupling scale A. Because then, if that's the case, roughly speaking, the energy, the infrared the running coupling is frozen at a very high scale, so we're starting with some asymptotically free theory, and the coupling at a very high scale will be weak. Okay. So I gave you this morning the form of the effective prepotential. So it looks like this, that there is first a perturbative term, which essentially was coming from integrating the one loop running of the coupling. As you recall, the second derivative of the prepotential is the effective coupling, plus, say, instanton corrections. Where k is the instanton number. So I introduced the dual special coordinate, a dual, which is given by the first derivative of the prepotential. And so if you do the computation, this is 2I over pi a log of a squared over lambda squared minus 2. plus non-perturbative corrections. Well, okay, let me ignore the instanton corrections and just write the approximate sign here. And so recall, A is not a gauge invariant variable, but we have a gauge invariant variable which is u, the expectation value of half trace pi squared. This is a good coordinate over the Coulomb branch, and for large A, it's approximately given by A squared, and then again there will be instanton corrections to this formula. Okay. So if I write everything in terms of the good coordinate u, this will look like 2I over phi square root of u log of u over lambda squared minus 2, again plus instanton corrections. And similarly, A, as I told you, is approximately given by square root of u. So now, so the Coulomb branch is parameterized by u, so it can be considered to be the u plane. So for very small, say, well, for values of u of order, yes? What's the question?
Was bless you.
So, deep within the Coulomb branch, there is going to be some region close to the origin whose size is order lambda squared, where the interactions will be strongly coupled, and we don't know yet what is going to happen there. Okay? But if u is very large compared to lambda squared, we can use the weakly coupled approximation. Okay? So let's consider the following loop at very large u. Okay, so we keep this loop at very large u. So we start, say, from a point in moduli space, and we adiabatically change the value of u, say, gauge invariant order parameter, until we get back to the same point. Okay. If this loop is very large, we can use the weakly, the perturbative approximation for the special coordinates. Okay. So like everyone is doing, I will denote this transformation where we adiabatically change u and bring it around in the u plane as follows. U going to the e to the 2 pi I u. Okay. So what happens to A and A dual when I do that? So A is approximately given by square root of u, and so this will get will pick a minus sign. Okay. On the other hand, A dual is given by this formula, so the square root of u in front will pick a minus sign, but then we'll also pick an extra spurious term from the logarithm. Okay. So this is 2I over phi square root of u log u over lambda squared minus 2, and this will go to minus 2I over phi square root of u log of u over lambda squared plus 2 pi I because of this change of phase minus 2, and this is equal to minus A dual plus 4k in terms of the original special coordinates. Okay? So we've learned that as we go full circle counterclockwise around u equal infinity, a dual A transforms as follows. And I will denote this. So a dual and A will keep what is called a monodromy. So I will denote this matrix, which we call monodromy matrix, by an infinity. So this is the monodromy matrix for the special coordinates a dual and A associated to a loop with a very large value of U. So a loop around infinity. So this is monodromy. So what we learn is that A and A dual are multi-valued functions, so they're not single-valued. Okay. So in particular, because of the logarithm here, and because of the square root, there are some branch cuts. So I should contrast this monodromy transformation versus the electric-magnetic duality. So when I stress that electric-magnetic duality transformations are just passive transformations, so they're changes of reference frame. Instead, here this monodromy transformation is an active transformation. So I adiabatically change the expectation value of trace phi squared in such a way that I went full circle around infinity. Okay. So this is a physical transformation. So in particular, this transformation doing this loop at u goes to infinity changes the central charge. And since the central charge is a physical observable, it determines the mass. This is an actual physical transformation.
Sorry, I'm not sure I'm understanding the difference completely. Couldn't you say instead that you're doing a change of theory definition and bringing your reference frame back towards to pi angle, and then the central charge is a redefinition of a coupling like tau?
Kind of, but okay. Except that, so if I start here, I start to change u slowly, the central charge and the mass of the state will change. Okay, and then so I end up there at what I thought was the same point, but A dual and A had changed and the central charge had changed. So the central charge is invariant under electric-magnetic duality transformations, which are just changes of reference frame, but here instead.
Yeah, but I was asking, couldn't you say that tau is invariant under this, but
okay, maybe you'll be satisfied by what I'm going to say in a second. So, okay, so I should stress again, so this is a physical transformation, so it changes everything. But you could say, alternatively, you could attribute the monodromy to the magnetic and electric charges instead of attributing it to the special coordinates. Okay. So here, A dual and A changed like that, and M and N were invariant. Okay. So, but alternatively, you can just move. Okay. So you can just attribute the monodromy to the charges. and say that a dual A are unchanged and M and N instead transformed by this monodromy matrix. Okay, so it's up to you, to use one description or the other description. The point is that the central charge, which is given by the inner product of these two objects, either if you use this description or that description, will change in an appropriate way. So in particular here, this is going to be equal to minus m, and for m minus n. Okay, so let me tell you a bit more about this monodromy matrix at infinity. So this monodromy matrix at infinity, minus 1 for 0, minus 1, can also be written as p times e to the minus 4, where p is minus the identity in a set to z, so you can think of this as a charge conjugation, and t is the usual t transformation. Yeah. So why does P appear there in the monodromy at infinity? So P is there already classically. So because, well, okay. Recall classically, A is equal to square root of U, exactly, and a dual is tau times A. Okay. So if you do this, if you follow this loop at special infinity, a dual and A classically will see the monodromy, which is just this matrix. Okay. And the idea here is that, say, A goes to minus A, then since the U1 field strength was defined as follows. Okay, obviously when A goes to minus A, which is what happens when we follow this monodromy, the field strength of the low energy U1 will change sign, so electric and magnetic charges will change sign, and they will transform like that. So instead, t to the minus 4, this is appears as a one loop effect. So let's call it one loop monodromy. And this is due to the one loop coupling, the one loop beta function coefficient, which was 2 and c equal 4. So this 4 here is the same 4 there. Because you see that is that just comes from the coefficient of the logarithm. And the coefficient of the logarithm is the one loop beta function. So you can also view it as due to the Witten effect. So in particular, say compute tau A is in the one loop perturbative formula. This will look like this over lambda, and this will transform to tau A minus 4. In particular, if you use the standard formula for transformation applied to this monodromy, this is what you get. Okay. But this is essentially due to the fact that as you go full circle around the u equal infinity, the theta angle as a function of A will go into the theta angle minus 8 pi. And this is 4 times 2 pi u to this t2 minus 4. I told you, so this is essentially, we can attribute it to the Witten effect because you see that there is a shift of the electric charge n by a multiple of the magnetic charge. This is due to the theta angle. Okay, so what we've seen here is just by looking at the weakly coupled region around u equal infinity. So we've seen that A and A dual are multivalued functions. So in particular, u equal infinity is a singularity. It's a branch point of the logarithm. Okay. So since it's a singularity and it's a branch point, there has to be at least another singularity here in the strongly coupled region because the branch cut must end somewhere. So what we're going to do next is try to determine the structure of singularities in this strongly coupled region after the break. Let's start. So I got the question, so let me explain one thing a bit better about this monodromy at infinity. So I just used here the perturbative part of the answer to deduce the monodromy, and the monodromy came from the log, which was driven by the one loop running of the gauge coupling and by the square root u. Okay. I disregarded the non-perturbative instanton corrections there. So you might worry that they might also contribute to the monodromy. But in fact, just by using the general form that instanton corrections must have, the form that I wrote earlier, you can check that whatever the coefficients in the instanton expansions, they will not these corrections will not change the monodromy. So the point is that just one loop perturbative running of the gauge coupling fixes completely the monodromy at infinity, no matter what exactly the instanton corrections coefficients are. So all right, so as I said, so we saw that there is a singularity at infinity in the u-plane. So this singularity is a branch point, so there must be at least another singularity somewhere in the u-plane, because the branch cut has to end somewhere. And we expect other singularities to happen in the strongly coupled region where this perturbative approximation does not hold. Okay. So now what we're going to do next is try to understand what are the singularities and the monodromies in the strongly coupled region. Okay, so this means the region where, say, u is order on the square. So there are three questions that we want to answer. So first question is how many singularities are there in the strongly coupled region in addition to the singularity at infinity? Second question is what are their monodromies? And the third question is what is the physical interpretation of the monodromies and of the singularity? Okay, so recall. So here the physical interpretation of the singularity and the monodromy at infinity is essentially just one loop running of the gauge coupling. Okay, so the first thing that we want to understand is how many singularities there are in the strongly coupled region in addition to the singularity at infinity. So here, it's important to keep in mind the R-symmetry group of the problem. So recall that we had classically a U1 R-symmetry, which is broken by an anomaly to Z8 R-symmetry. And then this was broken by U expectation value of trace phi squared to some Z4 subgroup. Okay, so in particular there is a Z2 subgroup, which is essentially the quotient of this Z8 by that Z4, which is broken. And a non-trivial transformation in this Z2 will act on U by changing sign to it. So essentially, the physics at any point U, at any point in the U plane here, should be equivalent to the physics at minus U. And in particular, if there is a singularity at some particular value of U, which is non-zero, there has to be another singularity at minus that value of U. So now, to answer how many singularities there are, let's first consider the simplest option. And the simplest option is that there is a single extra singularity, and this single extra singularity can only be at U equals 0. Okay, so John 1. So we'll consider one extra singularity at U equals 0. So again, it must be at U equals 0, otherwise there would be another singularity at minus U. So in this situation, if this is the case, then we have just two singularities in total, one at infinity and one at 0. Okay. So this possibly, looks like the best guess. Why is that? Because classically, U equals 0 is the same as A equals 0. So in particular, you don't get back to the scalar field. So the gauge group SU2 is not broken. So we'll have massless gauge bosons at U equals 0 for the whole SU2. And that will, the fact that you have some extra massless gauge bosons will lead to a singularity of the low energy effective action. Okay. And similarly, the central charge formula was something like this. Classically. So not only gluons, so gluons are massless, but also using this formula, all dyons are massless. So there are all sorts of massless states that we did not take into account in our low energy effective action, and so you might expect that that's the source of the singularity. Okay, so this was just classical analysis, but quantum mechanically, say U equals 0 means strong coupling. So you cannot use the classical intuition and these classical formulas to draw any conclusion. And in fact, there is a simple argument which excludes this option excludes the possibility of having a single extra singularity at u equals 0.
Stefano,
Yes.
so these massless particles, they all contribute to the same singularity.
Yes. So the idea is that, so we're looking for some infrared effective action. So, you know, in principle, this infrared effective action should come out, should result of integrating out all massive degrees of freedom, just keeping the massless fields. But suppose that, you know, at some specific value of couplings of moduli, here u equals 0, you have some extra massless degree of freedom. So you didn't know that it was massless, so you integrated it out. That would lead to singularities. And the idea is that when you keep into account, take into account all massless degrees of freedom, then the physics will be regular. If you forget some of them, you will see some singularity. So from this point of view, that will be the general physical interpretation of the singularities.
But doesn't somehow like the more massless particles you have, the more sort of the worse singularity would be, or something like that?
Yes, and in fact, in some precise sense, but yes. But in fact, I mean, well, so I'll argue in a second that this situation is not realized, and in fact, there is no point in the moduli space, no point in the Coulomb branch where you get massless gluons. And even more, when you take the final solution for the infrared effective action, it's possible to see that the point A equals 0 is not on the moduli space, on the quantum moduli space. Okay, so let's see why this possibility is excluded. So we're considering the situation where we have this singularity at 0 and the other singularity at infinity with some branch point here, some branch cut. And so when you go, say, around infinity, the monodromy would be due to this branch cut. So in particular, the monodromy around infinity is also equal to the monodromy around 0, because it can deform this contour from being very close to infinity to being close to 0. Okay? And now, note that A squared was not affected by the monodromy. Because A just picked the minus sign. So A squared is not affected by the monodromy at infinity. This is the only monodromy, so A squared is not affected by the monodromy. And so it's a good global coordinate on the Coulomb branch on the moduli space of vacua if this situation is realized. Okay. Because whatever path you follow along the U-plane, A squared will go back to itself, so A squared is single valued. Okay. So next, so we can write expressions for A dual and A. So again, A dual will start with some, it's one loop expression that I wrote several times, like that expression over there. Plus, there are some corrections, but now, so if because A squared is some good global coordinates, and because we know how A dual and A transform, one can conclude that the extra term goes like A times an entire function of A squared. So some function of A squared with no singularities. Okay? So we don't know the precise form of the function, but we know that there are no singularities. Okay, so and then okay, so you can check that just by this the monotony will be reproduced.
Sorry, integral is it entire? You mean an analytic?
Yes.
Yes. Okay. Fine.
Analytic and yeah, with no singularities at all.
Okay.
So holomorphic.
Holomorphic.
And, well, different people mean different things.
Yeah,
Holomorphic. So entire is means like holomorphic and no singularities at all.
On the old complex plane, like on the old Riemann sphere.
And the old Riemann sphere, yes. So in particular, you might also consider as, I mean, the role of you that the role that you played before now is played by A squared, because this is a good global coordinate. Okay, so now you can take these expressions and compute down the effective coupling. So this is just the derivative again of A dual with respect to A. So we do the exercise. So the first term was just the one loop term. And then if you differentiate the second term with respect to A, you'll get some other entire function of A squared. Okay, which I guess it's G plus, I don't know, 2A squared derivative of G. Okay, so just doing the derivative. And this. To be fully explicit, it's F, so it's still an entire function. Okay, but now here's the catch. So we're interested in the inverse square gauge coupling, which is imaginary part of tau. Okay, and we want this imaginary part of tau to be positive for unitarity. Okay, so for the kinetic term to be positive definite. But okay, so now the imaginary part of tau is in fact a harmonic function because tau is holomorphic. Recall, I mean, the real and imaginary part of a holomorphic function are harmonic. So here, holomorphic means you know, d bar tau equals 0. So in particular, d bar of imaginary tau is 0, and the same for real tau. So we don't care about this. Okay. So the imaginary part of tau is a harmonic function. But the harmonic function cannot have a minimum. Okay, I mean, assuming some global information. So imaginary part of tau does not have a minimum. Say on the U plane or A squared plane. And therefore it must become negative somewhere. Okay? But okay, when this happens, unitarity is violated, so that means that this possibility that there is a single extra singularity at U equals 0 is not tenable. I mean, it's in violation of unitarity. Okay, so the simplest option is excluded. Any questions on this? So
Sorry?
Yes.
What are the complex coordinates del bar and dio? And del bar?
so any good global coordinate, for instance, a squared.
Okay.
Or I mean, for u that I've used before, but for all purposes, you can use a squared in this argument.
Do you really need to add g? I don't know if I'm saying.
No, I mean, okay. So the other option is g is 0.
No, but I'm saying if it is if it has no singularity, both in 0 and infinity is a constant.
That is right. But okay, we already know that there is a singularity at infinity.
But for g, so g is not entire on the Riemann sphere then, right? It's entire.
No. This is the entire
Yeah,
Riemann
just-
sphere. But it's,
All the rest is okay. I'm just saying do you really need, because if it's a constant, then you can not bother constants.
yeah, that is fine. That's right. Okay.
One more question. I don't understand why you need singularity in the origin at all. Why couldn't the branch cut begin and end at infinity?
No, we're just okay. So we know that there is a branch point at infinity. So we know that there must be at least another singularity.
Couldn't it move all the way back to infinity?
There is a single infinity. Okay, so the U plane is a complex plane, but you should view it as compactified by adding the point at infinity. There is a single point, that's the Riemann sphere. So there is just one point at infinity. So there is no, say, plus infinity and minus infinity. Okay, but then
around.
Then going around you wouldn't find any cut because you go through twice the singularity. Or at least
I mean, if you have a cut, you need the branch points, right? So, sorry, what are you considering this situation? Where is that something like this?
Yeah.
Yeah, so as I was saying, you know, there is no cut.
But that's what he's asking. He's saying, why do we want to cut?
Because we know that there is a cut due to the perturbative answer.
Is that the question?
No, the question was why couldn't you do this?
Okay.
Yeah, because then okay, you can contract this away and there is no branch cut. That is just some property of the Coulomb function. So next, okay. So next we're going to consider the option where there are two singularities in the strongly coupled region in addition to the one at infinity. Okay. So, but before we do that, let's stop for a second and worry about the physical interpretation of singularities. So let me make this point now, because you might worry about this. Okay, so if we have a singularity of the low energy effective action, so this is a signal of a breakdown of our infrared effective action. And as I said earlier in my answer to Julia, that happens if there are extra massless degrees of freedom. So if they are massless, they should have been included in the infrared effective action, and if you don't include them, you will encounter singularity. Okay, so now the question that we want to ask is so which kind of particles or solitons can become massless. Okay, so the simplest option, which I already alluded to earlier, is that there are gluons say, W bosons becoming massless. So this is what happened classically at the origin of the moduli space, where the gauge group is not broken down to U1, so the off-diagonal component of the SU2 vector become massless. Okay, and I told you, so this can happen. So since these gluons, W bosons carry electric charges under the low energy U1 gauge field, this can happen at K equals 0. So now I should say, I mean, the argument is not completely strict. I mean, it's not really a theorem, but Seiberg and Witten propose a few arguments to exclude that this possibility can occur. So I would recommend you to go and read their arguments. But I mean, the basic point is to see if you know how much you're convinced by it. The basic point is that so if you have massless non-abelian gauge fields, you know, really massless at the quantum level. So because these are massless, and that means there is no scale in the theory, you would expect that asymptotically at low energy, I mean, at this point where non-abelian gauge fields are massless, so you expect that asymptotically there is a conformal, there is scale invariance and there is a conformal field theory. Okay. Some non-trivial infrared fixed point. But then if you put this requirement together with supersymmetry, a superconformal field theory with n equal to supersymmetry must have SE2R times U1 R symmetry. Okay. So one of the arguments that they put forward, which I think, well, I don't know, in some sense maybe it's the strongest argument, is that so you need the full U1 R symmetry. So in the theory that that we're studying, the pure SE2 gauge theory, so classically there is an SE2 times U1 R symmetry, but the U1 R symmetry is anomalous. So still, so if you imagine that there is a superconformal field theory sitting at this point A equals 0 in the moduli space, essentially there must be an accidental U1 R symmetry group that is accidental, I mean it comes out of nowhere. And okay, while this is in principle possible along the RG flow, it's hard to imagine how this can happen. And then, okay, they also strengthen their argument by considering I don't know, other possibilities and trying to argue them out. Okay, this requires knowing a little bit about superconformal.
I did not understand this.
Okay, so I'm telling you that if you require superconformal invariance, there will be SE2 times U1R. So in our theory, at the quantum level, we have SE2R, but we don't have U1R. We just have Z8. Okay?
And so you could argue though that you could have another U1, right?
So it has to be an R symmetry. Okay. So first of all, I mean, well, okay, this goes into some of the details of the other parts of the argument. So you might argue that Z4 R symmetry enhances to U1R. But okay, then if that is the case, then you can argue that since the field at trace pi squared is charged under U1R, I mean, it has a charge too, so in particular, it cannot acquire bed. I mean, there is this kind of, as I said, I mean, it's kind of a loose point in the argument, so they are not excluding completely as a theorem that this cannot happen. It's just saying, you know, it's hard to imagine, and they have, they're considering various possible situations and excluding them. I don't think, I mean, this in a sense is just kind of, you know, they're just arguing for it, they're not proving it, and then, okay, well, you can see that if you assume that the other interpretation, which I'm going to explain in a second, of the singularity takes place, then there are all sorts of self-consistency arguments that apply.
Sorry.
Yes.
Is it sensible to ask then what is breaking that symmetry? A equals 0. No, not the C2, really the gauge symmetry. Why do the W boson remain massive?
No, this is, so now we're considering the situation where they're massless.
And we're ruling it out. I mean, we're saying it cannot happen because otherwise there would be a singularity of 0.
No, they're ruling it out because there would be a singularity, but that would be associated to some conformal field theory, super conformal field theory, etc.
I'm getting it, but doesn't this mean that then it means that these gluons are either decoupled completely or massive? Otherwise, there would be this singularity in the effective action, and we're ruling it.
No, so the singularity. So here we're assuming that the singularity is there. I mean, now we're A equals 0, but so before we excluded okay, so let me add one thing. So we excluded the situation where there is a single singularity, except in addition to the one at infinity. But so you have the one at infinity, and you might have I don't know, say 3 singularities: one at u0, one at minus u0, and another at 0. Right? This has not been excluded yet. Okay, there are other arguments later on to see, but you might have such a situation. Okay, in that case, here, okay, so this argument is kind of trying to argue against the possibility.
Oh, yeah.
So the other option is that solitons become massless. So in particular, monopoles and dyons. Okay. And this will turn out to be the answer. So in particular, let me remind you that monopoles and dyons are, at least in BPS, monopoles and dyons sit in hypermultiplets. And the BPS, so in particular, their central charge will be given by the formula that I presented before. So n A plus m A dual, and their mass is the absolute value of the central charge. So a dion with magnetic charge m and electric charge m is massless when NA at a point in moduli space where NA plus MA dual vanish. So we'll get back later in a few minutes, or maybe tomorrow morning, to the question of how many singularities. So we have excluded the possibility of having just singularity at infinity and 1 at 0. So the next option, obviously, is 1 at infinity and 2 in the strongly coupled region, and that will turn out to be the correct answer. But before going back to the problem, so let's just consider the situation where there is such a massless dion somewhere in the moduli space. Okay.
Sorry?
Yes.
This formula, if for just a monopole, you say a monopole.
Yes.
For a monopole, will imply that m equals 0 or
no, m is the magnetic charge of the monopole.
Yes.
So m is magnetic and n is electric.
Yeah.
So a monopole would be, say, well, a monopole with single with charge 1 would be 1, 0. Okay, so that will be massless at the point where a dual is 0, because this term vanishes.
Yes.
Okay.
But a dual is no. Okay, I will assume it.
Okay. So now, indeed, let's consider the situation where there is such a dion of magnetic charge M and electric charge N, which becomes massless at some point in moduli space. And this point has to be such that NA plus MA dual, where A and A dual are the values of the special coordinates of those points, vanish. Okay, so now comes the important observation. So we can use SL2Z electric magnetic duality together with weak coupling results to compute the monodromy matrix. Let me call it Mn, where M and N are magnetic and electric charges around the singularity, where charge N, charge Mn dion becomes massless. Okay. So in particular, we can take M and N to be co-prime, the following, so the greatest common divisor is 0, because say if M and N, say if M N is some integer Q times M0 and 0, then if the dion charges Mn becomes massless, then also the dion which charges co-prime charges M0 and 0 becomes massless, so we can just look at this. And in particular, this object is just some marginally stable bound state of Q of the smallest object. So we can just focus on the case of co-prime charges. Okay, so next, so the next observation is that because M and N are co-prime, those are related by SL2Z to 0, 1. So we can pick an electric magnetic duality reference frame where this dion looks like a particle of electric charge 1. So, as I said, so let's go to a dual frame where the dion has, say, dual charges, say, M prime. So the dion originally had charges M and N, and in the dual frame it has charges N prime, which we take to be 0 and 1. Okay. So now let me call the electric magnetic duality transformation matrix A now. So I know that earlier I called the electric magnetic duality transformation M, but now I'm using M for the monodromy matrices, and we should not confuse them, so let's call it A now. Hopefully you won't confuse it with a scalar in the vector multiplet, which I also call A. So this is the electric magnetic duality transformation, and we need the inverse matrix, which is delta minus beta minus gamma alpha. So again, all entries are integers by charge quantization, and the determinant is 1. Okay, so we want to go to the dual frame where the dual charges are 0, 1. So this is given in terms of all the electric, magnetic and electric charges of a dion by electric magnetic duality transformation formula. This Mn delta minus beta minus gamma alpha, okay, which is also equal to delta m minus gamma n minus beta n plus alpha n. Okay, so requiring that the dual charges of the dion are, in this dual frame, the dion is electrically charged, will fix 2 of the entries of this matrix, of these 2 conditions. So at the same time, because this is an electric magnetic duality transformation, the special coordinates will transform into dual special coordinates, and those are related to all the special coordinates as follows. So, okay, this is alpha dual plus beta A, gamma A dual plus delta A. Okay. So, all right. So we can do this duality frame rotation and go to this dual frame where the massless dion is interpreted as a massless particle of electric charge 1. Okay. So in the dual frame, we have a dual U1 gauge theory with a massless hypermultiplet of dual electric charge 1. Okay. So in this dual frame, this theory is just n equal to superQED theory. Okay, just some U1 theory with a massless electron. Again, let me call it n equal to dual superQED. And so this is a very simple theory. In particular, we can compute the running of the dual coupling. And this is given by the standard one loop formula. Now the B coefficient, the one loop beta function coefficient is negative. And the formula for the running looks like this. So this is using one loop beta function. Okay. For now, since the theory is SQD theory with massless fields, so this theory is free in the infrared, but we will run to strong coupling at high energies, much like non-supersymmetric QED. So here lambda prime is the Landau Paul scale for this dual super QED. So it's the UV scale where the coupling diverges. Again, this is okay, and this is not easily related to the original dynamically generated scale lambda in the SU2 field. Okay, just some lambda ball. So this running gauge coupling in this dual super QED theory. And in particular, we can integrate it. So recall the complexified coupling is the second derivative of the free potential, and the dual special coordinate is the first derivative of the super potential. So just by integrating tau A prime, we can find a formula for the dual special coordinate in the new frame, in the dual frame, and this looks like minus IA over 2 pi. Sorry, I forgot to minus I A prime over 2 pi log of A prime over lambda prime minus 1. So this is just integration. Okay, so now A prime has a good local coordinate near the singularity where the diamond is massless. Let's call it U equal U0. So you can write, you would expect that A prime goes like U minus U0 plus higher order term. So you might also consider the case where here there is U minus U0 is raised to an higher power, but okay, you can follow the you can repeat the following analysis and exclude it a posteriori. Okay, so now we have this singularity at U0 in the U plane somewhere. So now consider going around the singularity at U0. So if we encircle U0, so that means that we send U minus U0 to e to the 2 pi I U minus U. I want to see if we pick up a monodromy. So A prime is linear in U minus U0, and so it will not transform, it will not pick up a monodromy. Instead, A prime dual, which is given by this formula, contains a logarithm. And so when you follow the logarithm, you plug this expression for A prime here, and you go full circle around U0, you will find that A prime dual goes to A prime dual plus A prime. So, as a consequence, well, let's just, you can check by using this formula that tau prime goes to tau prime plus 1 in agreement with the formula that we started with. So because of this logarithm, which is again one loop beta function now for this dual U1 super QED theory, we do pick up a monodromy, and the monodromy around U0 is given by, so, well, okay. I should call it, well, okay, let me explain in a second. So this is the monodromy matrix that we found here. So this is the monodromy matrix for U0 in the dual frame. Let's say in particular, this tells us that if there is a point in moduli space where there is a massless hypermultiplet of magnetic charge 0 and electric charge 1, if you go around this point in the moduli space, you will pick up this monodromy. And now let me give you an exercise. Okay.
Bring it on. Bring it on.
So the exercise is as follows. So use the SL2C electric magnetic duality transformation. That we use here. So we started from a massless dion of charges, magnetic charge M and electric charge N, and we moved to a dual frame where the charges are 0, 1. I told you what is the monodromy in this dual frame, and now I ask you, okay, do rotate back with an SL2C duality transformation to deduce that this matrix 1 plus Mn n squared minus m squared 1 minus Mn is the monodromy matrix around the singularity due to a massless dion of charges M and N. Okay. So in particular, if M and N are equal to 0, 1, this is the computation that we did, and in particular, if you specialize this metric, we will go down to the formula that we derived. But then since the charges Mn with M and N coprime are related to 0, 1 by duality transformation, if you undo this duality, you should be able to see that this is the general answer.
Could you please tell again why we should pick them coprime?
Yes. So if they're not coprime, you can divide by the greatest common divisor. Okay? Divide the charges by the greatest common divisor, you get a new dion with smaller charges, which is still massless at the same point in moduli space. So you can view, I mean, the dion with charges which are multiplied will become massless at the same point as the other one, and you can view the dion with multiple charges to be some marginally stable bound state of the one with smaller charges. So you just have to worry about the smallest, the dion with the smallest charges. Okay, so let me finish this lecture with a comment. The remark is as follows. So I told you that this is the monodromy matrix due to a massless dion, charges Mn. So under this monodromy Mn, let's see what happens to the charge matrix Mn itself. So this will go to Mn times the monodromy matrix. Okay, so now you do the exercise of matrix multiplication. And you will find that the magnetic electric charge vector is invariant. So the magnetic electric charge vector of the dion which becomes massless is the left eigenstate of this matrix. Okay, so the dion responsible for the singularity is invariant under monodromy transformation. Okay. And, well, okay, so this is just a mathematical factor, but now so the point is that this had to be the case because it's the only way in which the statement that this dion is massless can make sense. You know, if the dion is massless, but you go at the singularity, but you go around the singularity and it's transformed into a state with different charges, it doesn't make sense to say that that state is massless. Okay, so you get, you know, all the transformed state will be massless as well, and so on and so forth. Okay, so this tells you that. So when this happens, the dions with these charges will stay invariant, and also the massless states, and the ones with charges with different charges, which are say not eigenvectors of the monodromy matrix, will be massive instead. Will remain massive. Okay. All right, so let's stop here.